Okay, thank you very much for the invitation. It's great to be able to speak here. I have to say up front that it's 7 a.m. here, so I don't usually give talks at that time of the day, so I guess we're just gonna have to try it and see how it goes. I'm gonna talk about some questions involving cyclotomic divisibility. Basically, that there's a whole range of questions that involve many different problems. You could talk about integer tilings. You could talk about something called the Favard length in geometric measure theory. You could talk about vanishing sums of roots of unity. What all of them have in common is that at the bottom of it, there's a problem that involves simultaneous divisibility of a polynomial by several cyclotomic factors. And I want to talk about some of these questions and the progress I was able to make on that with collaborators. If you don't know what any of those problems are right now, then that's fine. I'm going to try to explain everything. Right now, I just want you to keep in mind that there are going to be several of them, and they are going to be connected to each other. So let me start with integer tilings. I'm going to be interested in tiling the set of integers with translates of one tile. There are also interesting questions about tiling with more than one tile and tilings that involve mappings other than translations, but I'm not going to get into that right now. So here's the problem. Let's say that A is a finite set of integers. I'm going to say that A tiles the integers by translations if I can cover Z by a union of disjoint translates of A. So in other words, there's an infinite set T that's called the translation set, so that every X in Z can be expressed uniquely as X equal to A plus T with A in A and T plus T. So here are a couple of examples. If you take the set 0, 2, then you can just put one more translate of it at 1 and 3 and then keep repeating the pattern, and that's a tiling of integers. Same happens for any set of 2 elements. If you take 0, 4, 8, then that also tiles the integers by translations. You could do the same sort of thing that I did for 0, 2, so put the next copy at 1, 5, and 9, and then repeat that pattern. Or else you can observe that 0, 4, 8 is a complete set of residues mod 3, so you can just repeat that pattern, and that's going to be a tiling of period 3. The set 0, 1, 3 does not tile because there's no way to plug the gap at 2. So how do we determine whether a given set tiles the integers? If you have 2 or 3 elements, it's easy to just sort of try a couple of things and see how it works. If you have a set of, let's say, 30 integers somewhere between 0 and 10,000, then a computation that's going to be a much more difficult problem. And so we would like to have some sort of a way to determine things like that without having to do all those computations. There are some reductions that have been known for some time. One is a classic result due to Newman. This is based on just pigeonholing, and it says that all tilings of the integers by a finite set are periodic. And that reduces the problem to tilings of finite cyclic groups with addition mod n. Newman's estimate of the tiling period was not optimal. It's what you get from the pigeonholing argument. There is now a better one due to Greenfeld and Tal, but that's a whole different story. Another reduction is that we can assume that the period of tiling M has the same prime factors as the cardinality of A. This is due to Coven and Meyerowitz 1998, and that's based on an older theorem of Tiedemann. And there's also a reduction due to Sands, which says that A plus B is a tiling of Zm if and only if the product of the cardinalities is M, so that's the correct counting. And also we need the divisor sets of A and B to be disjoint except for M, where the divisor set is the set of all greatest common divisors of A minus A prime with M, A and A prime being elements of A. We're going to represent tilings as multidimensional structures as follows. So write M as a product of prime powers, and by the Chinese remainder theorem, we can write Zm as a product of the corresponding cyclic groups with orders P1 to the N1 and so on. That can be represented geometrically as a k-dimensional lattice, and then A plus B can be interpreted as a tiling of that lattice. But I want to emphasize that this is more than just a tiling of a multidimensional lattice. It's actually important that we have different primes in different directions. And if we looked at the corresponding problem for just a tiling of ZK, for example, then that would be a whole different question. Here's an example of how we represent sets in several dimensions. So for example, we have an arithmetic progression of step M over Pi. Here, this belongs to something that we call a grid at the top level. On the right, you have also an arithmetic progression, but this has step M over Pi Pj. So that's the sort of thing we're going to be doing. And so here are some examples. These are all in 2 dimensions, just because that's easier to draw. At the top, you have tilings that look relatively simple. So you have a lattice for A and another lattice for B with different steps. The red points represent A, blue points represent B, and there's one green point in each picture, which represents a point that belongs to both sets. And so we start with the tilings here at the top. Those are kind of nice and regular. And then we try to look at how we can mess them up and still preserve the property of tiling. So at the bottom, in the middle row, we messed up B here a little bit. We kept A the same, but we shifted around some elements of B. Here we shifted some elements of A, and similar modifications in the pictures here at the bottom. Here we shifted part of A and part of B. And so if you do that and you try to look at what patterns come up, you can see that the more you mess up one of the sets, the more rigid the other one has to be. If your B is kind of all over the place, like in the picture here, then A actually has to be the lattice that we started with. And that's something that's important in our work. It's actually something that has to happen. Okay, here are some examples in 3 dimensions. One example, actually, A is a lattice in 3 dimensions. So that the whole picture on the left is A. I just use different colors to indicate different layers of it, and B is the set on the right. And then we can also check that that is a tiling. I was going to talk about cyclotomic polynomials. So let's first introduce the polynomial formulation of tiling. We may assume that both sets are contained in non-negative integers. That's by translational invariance. And then we can define the mask polynomials or characteristic polynomials by saying that a of x is the sum of x to the a, where a runs over all elements of a, and likewise for b. And then the tiling condition is equivalent to saying that a of x times b of x is 1 plus x plus and so on plus x to the n minus 1 mod x to the n minus 1. And this is where we can use factorization of polynomials. The S cyclotomic polynomial is the unique monic and irreducible polynomial whose roots are the primitive S roots of unity. An alternative definition is by induction. We factorize x to the n minus 1 as a product of irreducible factors, and then the factors of that are going to be exactly the cyclotomic polynomials phi s of x, where s ranges over all divisors of n with 1 and n included. Then the tiling condition here is equivalent to saying that a times b cardinalities are correct, and phi s divides a of x times b of x for all s dividing n and different from 1. We lost 1 because this 1 plus x to the n minus 1 is equal to x to the n minus 1 over x minus 1. And so x minus 1 gets deleted. Everything else still has to be there. Because the cyclotomic polynomials are irreducible, each one has to divide at least one of A and B. And so here are tiling conditions that were proposed by Coven and Meyerowitz in 1998. Let's define S of A to be the set of prime powers such that phi to the phi p alpha of x divides a of x. And then we have two conditions. One is that a of 1 is the product of phi s of 1 with s in SA. And the other concerns divisibility by mixed cyclotomics corresponding to products of the prime powers in SA. Then these two conditions imply that A tiles the integers. If A tiles, then we have the first condition. And we also have the second condition if A has at most 2 prime factors. The first condition, T1, is basically just a counting condition. The second one is more difficult. This is a structural condition that has been difficult to prove in general. Coven and Meyerowitz proved this for 2 prime factors, and that was based on a reduction due to sense, which is in that setting, if you have a group Zm where M has at most 2 prime factors, then one of the sets A or B has to be contained in the subgroup. This is not true when you have more prime factors. If you had trouble parsing that second condition, which I would not be surprised because I had a lot of trouble parsing that condition when I first started reading about it. Then here's a more geometric interpretation of the same condition. So let's assume that we have a tiling A plus B is Zm. And based on that tiling, we can define something called the standard tiling set. There's an explicit formula for it, which I wrote here. It's based only on the prime power cyclotomic factors of A. The point is that this is a set that has the same prime power cyclotomic divisors, but also it has the lattice structure from the previous picture. So the condition T2 is saying that if B satisfies T2, then that's true if and only if I can replace its tiling complement A by the standard tiling set. And that's a little bit similar to the theory of replacement of factors in the factory of group factorization. And there's a whole different research area with many papers and books and things like that just about this. So that's a whole other topic that I don't want to really start. Anyway, the point is that this is kind of the geometric meaning of T2. The result that I proved with Itay Londner last year is that if the tiling period is P1, P2, P3 squared, and that's the simplest case that cannot be reduced to prime factors using subgroup reductions, then A and B both have to satisfy that condition. Additionally, we have what's basically a classification of all tilings of that period. It does not get much more complicated than examples due to Szabó. And I'm gonna show how that works in a moment. And also the methods and some of the intermediate results extend to more general. Okay, so here's why three prime factors are more difficult. I said earlier that when M has two prime factors at most, then one of the A and B sets has to be contained in a subgroup. This does not have to be true for three prime factors, and an example of that is due to Szabó. I'm actually going to show you a modified version of that example in the formulation due to Lagarius and Szabó a little bit later. So we start with a standard tiling where A and B are both lattices. A is a lattice on the big scale and B is a lattice on the small scale. And then I'm going to start shifting columns in A. So first, I'm taking the column in the corner and shifting it up, not quite by a full step in the lattice, but by some intermediate step on a lower scale. And then with that done, there's a column at the bottom of the picture that gets shifted in a different direction, also by like a half step. And then there's also a row at the top that gets shifted in the third direction. And in 3 dimensions, it's possible to do all 3 of those shifts without destroying the tiling product. So if you want to look at the video for a moment, then this is my favorite toy to demonstrate that sort of thing. This is my tiling. Each little cube represents the B set. And so I'm going to shift one column, let's say like this. And, sorry, it's supposed to stay here for now. And then another like this, maybe. And then I can still shift this one here. And so that's my set. Okay, so the ideas that we need to solve the 3' factors are as follows. Let's start with the assumption that phi m divides A. It has to divide one of the sets, A or B, so let's say it's A. We use this to establish some initial structure. At first, it's just going to be on top level grids. And then we try to use that to recover more of the set A. We now have two cases. One is when all grids are something we call fibered, which means they have a nice structure. We then use it to do a sort of induction on the scales. In our case, we only have like 2 scales, so that's not that much induction. But the problem is that the grids can be fibered in different directions, and so that makes it more difficult. For unfibered grids, like in this example, we use the irregularities to recover the rest of the tiling. So what we do with that is, if you want to look at the video again, we start with an unfibered grid, which is basically this, except at first I do not see the whole picture. I just see something like this, with all the shifted columns missing from it altogether. And then what I need to do is I need to prove that those shifted columns actually had to be there. And then I need to prove that I can shift those back in place and maintain the tiling property. So let's see if we can do that. There's one here, so I'm going to shift it back in place. And then there was one missing here, and I'm going to shift that back in place again. And now I have a nice lattice tiling, and I know everything about it. So that's kind of a toy version, literally, of what happens in the paper. To do all of that, we needed to develop a lot of new tools, so that there's something called the box product, that there are multi-scale cuboids, we have something called saturating sets, and so on. I'm not going to explain all of those, but I do want to mention that those can be applied to other problems, and this is not just excuse me, that this is not just kind of hoping that this can be hopefully applied to something that we hope is going to be interesting, but I already have a couple more applications that I'm going to tell you about in the rest of the talk. So I don't know, maybe this is a good time to ask if anyone has questions before I move on to the next thing. Okay. I want to mention something called Fuglede's spectral set conjecture. The conjecture is about tilings in all dimensions, so that's an example here of a tiling that I found on the beach last year. The conjecture is that a domain in Rn, we assume that it has non-zero and finite Lebesgue measure. The conjecture is that it tiles Rn by translations if and only if the L2 space on omega admits an orthogonal basis of exponential functions. This is known to be false in general in dimensions 3 and higher. The first Cantor examples were due to tau and then extended by several others. It's true, however, in many special cases of interest. So, for example, it's true when the translation set is a lattice. It's true when we look at convex sets in 2 dimensions. That was proved by Josewicz, Katz, and Tau 20 years ago, and then the proof for higher n was given only very recently by Greenfeld and Lev in 3 dimensions, and then Lev and Matteucci for higher n. There's also a lot of interest in the finite group analog of the conjecture, and there are results on that due to a number of people in the last few years. So we need the group to have simple enough structure. The obstacle in extending the tiling implies spectrum direction is the T2 condition, basically, and more on that in a moment. But there is also a lot of work on proving the spectral implies tiling direction for various relatively simple groups. Okay, so the connection to the tiling conditions that I talked about earlier is that first of all, T2 implies spectrality in various settings. I proved it for unions of finitely many unit intervals in R, but the same result with the same proof is also true for tilings of finite cyclic groups. And together with earlier work by Lagarius and Wang, this implies that we have a reduction of the spectral set conjecture as follows. Suppose that T2 holds for all finite sets, the tile integers by translations, then every bounded tile of R is spectral. Lagarius and Wang reduced the problem to unions of finitely many unit intervals, and then if we had T2 for those, then that would resolve this part of the problem. There is also a sort of a converse due to Dudka and Lai. If every spectral set of integers satisfies T1 and T2, then there's a reduction in the other direction. The connection is through an explicit, the connection from between T2 and spectrality is that if you have the T2 condition, then you have a bunch of cyclotomic polynomials that divide A of X, and those polynomials have a nice structure. And you can use that to construct an explicit set lambda so that the corresponding set of exponential functions is in orthogonal basis. So the corollary of the tiling result that I mentioned is that we have the tiling implies spectrum part for the group Z Ti squared, Pj squared, Pk squared, where Ti, Pj, Pk are distinct primes. We don't know yet whether there's going to be an implication in the other direction. Spectrum implies tiling, but I know of at least one group of people that's planning to work on that. Okay, so the next question that I want to talk about is vanishing sums of roots of unity. This is a classic area of work in combinatorial number theory. So here's the question. Let's say that Z1 to Zk are, excuse me, are nth roots of unity, not necessarily primitive, and suppose that they add up to 0. So under what conditions does that happen? For example, if you take the fifth roots of unity, like in the picture, then they add up to 0. And same is going to happen if you take all pth roots of unity for any prime p. And can we come up with other examples that do that? So it turns out that, that there's a theorem that's been known for a long time. This is due to Rede, De Bruyn, and Schoenberg, with a complicated history. Any vanishing sum of that form can be expressed as a linear combination of rotated prime polygons, like this, with various primes, with integer coefficients. Integer, but not necessarily positive, meaning that we allow cancellations between the polygons. There are further proofs of that theorem by various authors, and there are also results on classification of vanishing sums of that form with a small number of roots. So there are some papers in computational number theory that do that. The connection to cyclotomic divisibility is that, let's say that a of x is a polynomial of this form here. And then we have a vanishing sum of roots of unity here of nth order with some coefficients a, not necessarily relatively prime to n, if and only if a of 2 pi I over n is 0, and that means that phi n needs to divide a of x, because phi n was the minimal polynomial of e to the 2 pi I over n. And so we are again looking at divisibility of polynomials by cyclotomic factors. A result that I'm going to be interested in is a theorem due to Lam and Lang from about 20 years ago, which says that suppose that Z1 plus and so on plus Zk is 0. The Zj's are nth roots of unity, and n is a number like this one, with prime factors p1, p2 up to pk. Then to get a vanishing combination of roots of unity, the number of roots that you need to use has to be at least the minimum of the prime factors of n. An equivalent formulation in terms of cyclotomic polynomials is that if a of x is divisible by phi n, a here is a mask polynomial of a set, then the cardinality of a is bounded from below by the minimum of, again, the prime factors of n. So what I'm going to be interested in is, can we improve that lower bound if a of x has more than one cyclotomic divisor? Why I'm interested in that question? Actually, part of that is that this is going to be used in the next question that I'm going to be talking about, and that one comes from harmonic analysis. But right now, let's just say that I'm interested in this. Let's say that a of x has more than one cyclotomic divisor. Can I improve the lower bound due to Lam and Lang? Turns out that in general, this is not possible. And so if I take an A of the form given here in the explicit example, then this has a lot of cyclotomic divisors. Specifically, I could take phi p q to the alpha for all alpha between 0 and n. So n here can be as large as I want, but a of 1 is still p. So no improvement like that. However, there's also an easy case when we do get an improvement. If we have several divisors where the Sj are all prime powers, then phi p to the alpha of 1 is always p. And so we get an improvement here. The argument does not work when the Sj are not prime powers, because then phi evaluates to 1 at 1. So a result that I proved with Laba-Marshall is that suppose that you have multiple cyclotomic divisors as phi s1 to phi sk, where all of the s1 to sk have at most 2 prime factors p and q, and those factors need to be the same for all of the s's. A may also have additional cyclotomic factors that are not of that form that's permitted, but it does not enter the considerations. If we assume that Q does not divide the cardinality of A, then the cardinality of A has to be bounded from below by P to the EP, where EP is the number of distinct exponents of P in the factorization of S1 to Sk. The assumption that Q does not divide A rules out the example from the previous slide where we did not have an improvement. And the prime power example shows that this bound is optimal, and we cannot have any further improvements without additional assumptions. Let's see, before I move on to the last topic, I'd like to stop asking if there are questions. Okay, so now I'm going to talk about a problem from harmonic analysis and geometric measure theory, which is what actually led me to the vanishing sums of lots of units. So we start with something that at first sight might not look related, and that's the Favard length problem, which is as follows. Let's say that we have a self-similar Cantor set in the plane. Assume that the set is purely unrectifiable, has Hausdorff of dimension 1. And what's the average with respect to angle length of linear projections of the finite iterations of the set? And a slightly more precise formulation is as follows. Define the projection in the direction of theta in the xy plane. So that's the usual expression that you know from calculus. And then for a self-similar set, we take the finite iterations of that. That's En. We take the projections of En in the direction theta. We figure out the length of that, and then we compute the average of it. A theorem of Vesicovich implies that this goes to 0 as n goes to infinity. the question that we are interested in is the rate of decay. So here's an example. This is something called the four-corner set, which comes up in various parts of harmonic and complex analysis. I want to look at projections of that set in various directions. So if I take, for example, a projection on a horizontal line, then I'm just going to get a Cantor set like this. The set here is obtained by taking the four squares here, then iterating the construction and so on. And as a projection in this direction, I get the Cantor set where I'm taking these two intervals, then iterating that construction and so on. And so that's actually going to have Hausdorff dimension 1/2. So that's going to be a very small projection. However, there's also a direction like, let's see if I can do this correctly. Let me try to draw a line. Let's see. Okay, I think that's about right. So if I take a projection in that direction, then what I'm going to be getting is that the projections of the different squares actually meet each other like this. And so the set is actually going to project to a full line segment from here up to whatever the other endpoint is going to be. And then as I continue to iterate the construction, this is not going to change. I'm still going to get the full line segment. And so the projections can vary a lot between the directions. And what I want to prove is that if I take the average over all angles, then that average is going to be better behaved. I also want to look at more general product Cantor sets, where instead of a 4x4 square, I start with an L by L square. L is going to be a positive integer, at least 4, divided into L squared congruent squares of side length 1. Choose digit sets A and B in each direction, and then keep the squares whose bottom left vertices have coordinates in A cross B, and then iterate that construction. So this would be a product set with L equal to 4 and A and B both equal to 0 and 3. There are various results on the Favard length of those. There's a general lower bound C over N due to Matila, and an improved lower bound for the four corner set specifically, C log N over N, that's due to Bateman and Wahlberg. And there are also various upper bounds. The first one of those was the bound for the four corner set due to Nazarov, Perez, and Wahlberg. And then that was extended to various classes of sets by various authors. So what Caleb and I were interested in doing was extending this last result due to Bond, Wahlberg, and myself to more general Cantor product set. This one applied to sets where the digit sets have cardinality at most 6. And the obstacle was cyclotomic divisibility. So the result that we proved is that the estimate extends to, first of all, cardinalities at most 10. And we could probably extend it a little bit beyond that, but it's just really annoying to have to go through so many special cases. So we stopped at 10. And we can also extend it to the case when we have control of the cyclotomic divisors of A of X, where S is relatively prime to the cardinality of A. This is a typo. That should be the cardinality of A and not the set A. And the same condition for B. And there's also a further improvement if A of X and B of X have no roots on the unit circle of the form e to the 2 pi I lambda with lambda irrational. The main obstacle to extending that estimate to all product Cantor sets involves cyclotomic divisors of A of X and B of X. And specifically, the divisors that cause trouble are those with S relatively prime to L. That affects the behavior of certain Fourier transforms that we have to compute. Basically, we take the projected one-dimensional Cantor measures. We have to compute Fourier transforms of those. That involves a bunch of cyclotomic trigonometric polynomials. And then that's where you run into trouble. And turns out that what we need to be able to control that sort of thing is an effective version of that theorem I mentioned earlier about vanishing sums of roots of unity. So the enemy is basically the case when we have a lot of polygons with large primes involved, with a lot of cancellations between them. So many complicated structures with a lot of cancellations adding up only to a few non-zero terms. And this is the sort of thing that we do not want to have. And that's how we ended up getting interested in proving an effective version of that theorem, and therefore improving the Lamont length lower bound on vanishing sums of roots of unity with more than one cyclotomic divisor. If we have only one cyclotomic divisor, then we can solve the Cantor set problem, and actually that was already done in the problem in the paper with Bond and Wahlberg. The problem is that you may have many different cyclotomic divisors. Okay, so to get past the obstacles, we need to construct something called the set of large values. The general approach was initiated in the paper with Bond and Wahlberg. We have to modify the construction based on an appropriate grouping of the cyclotomic divisors. And then we need to combine that either with the lower bound theorem, or so that's for the 2' part of the result, or else we can combine it with the explicit classification of vanishing sums with few elements, and that would be something that we can borrow from the paper by Pullman and Rubinstein. Okay, thank you for your attention.